All right, we'll go from current slide. Okay, let me go over announcements first, and then we'll talk about how the term's going to end. Okay. This needs to go down. Well, actually, this can just go into the trash. There's no reason to. Okay. I don't know if y'all have, I can't remember if I think I've made these some of these announcements before, but in case you didn't realize it, last year's volleyball team was the best in school history, had the best record, most wins, and they were really outstanding. We got probably close to half of them back this year, and a new group of recruits, same coaching staff, so I bet you they're not very good this time as well. Not talking about, right, no, I am, I'm sorry. Okay. All right. So if you have a chance, well, no, you won't have a chance. Well, you might get the last part of it, okay? They have a match this afternoon at 5 o'clock, so if you finish things soon enough, which I don't think you will, you can still, if it's a 3-game set, you can probably catch the third one. But it's a home match. It's versus Coastal Alabama East. Evidently, Coastal Alabama has a South volleyball team and an East volleyball team. I guess there's no West or North, but they've combined a lot of schools into bigger, merged colleges. And I guess 2 of the colleges had programs, so they just kept them, named one the East and one the South. So anyway, we're playing East today. And that's on the Birmingham West Campus, Arthur Shores Fine Arts Building, which is also our gymnasium. And that's at 5 o'clock this afternoon. So that's when it starts. I bet it'll still be going on about the time y'all are leaving here if you want to run over there and catch it. Now, tomorrow, they're playing Bevel State, but I'm sorry, I'm on the wrong one. Gadsden State in Gadsden, so that's going to be a bit of a stretch to get to that one. That's the 6 o'clock match. And then I'll tell you the rest of those Thursday. College Scholars Bowl. College Scholars Bowl is still seeking recruits. I assume so anyway. Yes. Okay, still currently recruiting players with a knowledge in any subject, including history, literature, science, music, current events, mythology, and mathematics. I sort of wish they didn't put mythology with mathematics. But anyway, the coach is Mr. Matthew West. If you go down the half flight of stairs, 259 was where we had a lab a week or so ago. And the door just past that, between that and 261, that's his office right there. Okay? Now, he's on the Birmingham campus quite a bit, too, but that's his office. Check in with him. Check in with either of you two, like Ian and I'm going blank on your name right now. Tell me. Amanda. Okay. Yeah. Okay, Amanda, and then... and they can give you more information as well. Another thing that, great opportunity, is the NASA Community College Aerospace Scholars Program. We've had several Lawson students participate in this, and all of them have spoken incredibly highly of this program. It's a great opportunity. Sometimes they actually get to interact with the astronauts on the space station. I mean, it's just a really interesting, enlightening way to learn fun stuff. And if you want more information about it, the website is go.nasa.gov. Then there's all sorts of suffixes you can put on that to take you different places. But they will be accepting applications through October 16th, which is right around 3 weeks away. So take advantage of it. It's a great program. All right. Has anyone else come in since I called roll? I don't see. About 5, 9, 2, 3, 4, 5, 6, 7, 8, 9. Yeah, got everybody here so far. All right, now let's talk about how we're going to wrap up the term, even though we've got 3 weeks left and only 2 chapters left. And Ian was griping that we skipped 2 chapters, so you can take your gripe up with him. Okay, no, okay. We'll get going on chapter 23 today. I don't know that we'll finish it. It's a fairly long chapter and relatively involved. And most of you have the books that don't even have chapter 22 in it. But if you wanted to read up on our atmosphere, that's what chapter 22 was, and most of the time we don't have time to do that chapter. So if you want to read up on that, that gives you a good background for what we're doing now. Anything we run into that you need to know stuff from there, we'll talk about it in this chapter. But this chapter is weather and climate. So if we do get well into 23 today but don't finish, then we'll probably be wrapping up 23 on Thursday. The lab for this is the field trip. So I don't think we'll be able to be at the point that we want to take the field trip by Thursday. So the likelihood will be I'll start making arrangements for next week, either Tuesday or Thursday, whichever day looks best for Jerry Tracy or whoever on his staff will be hosting us. And I'll give him the option of when and that type of thing. So 23 today, but before the end of the day, we have the test from chapter 20. Okay? So hopefully you have your formula and equation sheets ready for that. That was the shaping Earth's surface. Okay? What's that?
Is the test multiple choice?
Oh, mostly multiple choice. It's not like the chapter 19 test, which you take on this. It's more like the others have been. Okay. Probably will be a couple of fill in the blank, but not that many. I don't remember anyway. Because we got plenty of time, we'll probably end the chapter a little earlier to give everybody all the time they need on the test. So there shouldn't be any time pressure at all on the test. And some of you may actually, finish early and get to go a little early. Okay, Thursday then we'll probably be finishing chapter 23 and then perhaps starting 24. Okay, again, there's no rush. So what we'll probably do then is hopefully have the field trip either Tuesday or Thursday of next week, and the other day we'll be finishing chapter 24. Tentatively now anyway. There is a lab for 24. We'll do it in class. It's a paper lab, and you'll just work on that. And then the final exam will be, I think, Thursday of the following week. Okay? So that gives us plenty of time for this. If we have extra time, then anyone who wants to do a report on his or her research paper, that can be an optional lab for you. And just do a report on it. 5 to 10 minutes is all we'll need. And we'll take up as much class time as we need for that, class or lab time. Because we're ahead of schedule. Any thoughts? And then too, what we might have is an optional lab day sometime. Perhaps the last Thursday afternoon, if we're finished with everything else. Anyone who hasn't done a lab that wants to make up a lab can do that. And we do have several who haven't. Which, now that I'm on that subject, let me go on and hit it. Okay, research papers, I've gotten 4 in out of my best class ever of 26 students. So that's less than a quarter of you have turned in a research paper. Please get those. Well, I got in another one today, didn't I? I think so. Somebody turned one in. Okay. Lab 1, still missing, I'm preaching to the choir here, still missing 3 lab 1s. Test 1, missing 2, no. Yeah, missing 2. Lab 2, missing 1, 2, 3, 4. Test 2, missing 1, 2. Lab 3, only got 2 in, so get those in, folks. Well, I may have gotten some in more in today. Okay, test 3, missing 1, 2, 3, 4. Lab 4, missing 1, 2, 3, 4, 5, 6, 7, 8. Test 4, missing 1, 2, 3, 4, 5, 6. Lab 5, missing 1, 2, 3, 4, 5, 6, a bunch. That's the one that had questions with it, so only less than half of you have turned in the lab and the questions. Test 5, missing 1, 2, 3, 4, 5. Lab 6, missing 3, 4, 5, 6, 7. Test 6, barely half of you took that. And lab 7, just over half of you have turned that in. Of course, those aren't due yet, so again, I'm probably preaching to the choir. I think most of you are pretty close to being up to date. So, sorry about that. But I'm recording this, so hopefully if anyone's listening, they will hear that as well. So, we're talking about weather and climate. This time, this is the order we're going to cover it. The chapter split, and not dead down the middle, but pretty close to about half of it on weather and about half of it on climate. Okay? We'll talk about the difference later. The core concept, which you can find on page 573 of the big book, or whatever that is on your smaller books, solar radiation drives the cycles, boy have we had cycles in just about every chapter, in Earth's atmosphere, which was what the last chapter talked about, and some of those cycles determine the weather and the climate. Okay? Now, this is a picture here. It's not in your book, but it's from an earlier one. This is probably a satellite photo, or at least a very high-range aircraft photo of basically the Gulf of Mexico. This is the Panhandle of Florida, or the Peninsula of Florida. This is Cuba down here. This somewhere under there is Louisiana, I think. There's cloud cover here, so it's hard to say for sure. This, I think, is the coast of Texas and into Mexico here, and there's where Yucatan Peninsula comes up from the Gulf. So this is pretty much major shot of the Gulf of Mexico. Obviously, some stuff's happening here. Clouds, pretty dense in here over the land, but a little bit over the sea as well. Different things going on in the country. You can almost see, this looks like waterways, but it's probably cloud formation is what you see there, with a lot denser clouds over part of the land. We won't go into everything there, but we will be able to interpret some things as part of this. It just shows that what's going on in the atmosphere is largely driving the rest. And Luis snuck in while I wasn't looking, but I caught you. Okay. And anyone else come in since I called roll. All right, so let's start in 23.1, clouds and precipitation. I think everybody pretty much knows what a cloud is, right? What is a cloud?
It's that scary white thing in the sky.
Oh, okay, that thing, okay. What's it made of? Water droplets. That's what makes it that white thing. That's what reflects the sunlight, unless you're underneath it, and then it looks pretty dark because it blocks the sunlight. I bet you everybody thinks they know what precipitation is, too. What is precipitation? rain is one type of precipitation. What precipitation means is falling out. Okay, think of a precipice. You could fall down a precipice, a crack or something. Okay, precipitation is anything that comes down. In chemistry, I can remember when I was a little bit in the same neighborhood of age as some of you. My first quarter of chemistry at Georgia Tech, first quarter I was there, Chemistry 1. The first lab we did, we mixed silver nitrate with calcium chloride, I think it was, something like that. They were both clear liquids, perfectly clear liquids. Once you put a few drops of the silver nitrate into the solution of calcium chloride, all of a sudden white stuff started falling out of the solution. That was called a precipitate because it fell out of solution. Because silver chloride is not soluble, silver nitrate was. So precipitation is anything that falls out of the sky. That would be rain. It could be snow. It could be hail. Could it be dew? Now, dew is a surface phenomenon. We'll get to this later. Frost is a surface phenomenon. It doesn't fall out of the sky. It happens on the surface. So we're talking about clouds and precipitation. But before we get that far, let's go over another cycle. Okay, we've had rock cycles. We've had lots of things that go through passages like this. The hydrologic cycle. What is hydrology? What does that have to do with? Water, exactly. You can think of water as good old hydrogen oxide, right? H2O, hydrogen oxide. So hydrologic cycle. So let's take a look. I think we've got a visual coming up. It's a cycle, so where does it start? Where does it end? It's a cycle. So let's just start in the ocean. That's where most in the next chapter we'll be talking about this. Huge surface of the earth. More than 2/3 of the surface of the earth covered with water. Okay? Covered with water. Mostly from the oceans, but also from lakes and gulfs and seas and all sorts of other, lots of water covering the surface of the earth. As the sun, the solar radiation hits this, it evaporates the water from the oceans. Now, some areas don't evaporate as much as others, but large areas of water, the water is evaporating. It goes up into the air. Now here you don't see it generally, okay? This is invisible. It's evaporating. It's just like when you're boiling that water on the stove. You might see steam for a little bit, but then the steam, you don't see it after a while. It mixes into the air, okay? Maurice, right? Okay. Now, so the water evaporating into the air, going up into the air, because it's warmed up, that's why it goes up. Okay? Camera? Okay. But as you go higher and higher into the atmosphere, at some point, pretty quickly, you start getting cooler temperatures. Even though on the surface of the water may be quite warm, somewhere up there it starts cooling off. And where it starts cooling off, now the water begins to condense. Okay? We'll get to that a little bit later. The condensation is what makes the clouds. The water droplets, those are water droplets there. Evaporated water, you don't see at all. Okay? So, those clouds now get moved through the atmosphere. Now, a couple of reasons that the clouds move through the atmosphere. What we have is a fairly contiguous sphere here that is the Earth, right? And that Earth is spinning, of course, right? Okay? Now, as that Earth spins, okay, there's an atmosphere surrounding it. Now, the atmosphere is not attached to the Earth, okay, obviously, okay? It's air, it's gas, okay, not attached. So therefore, the Earth tends to spin underneath the atmosphere. Now, we're on the Earth, and we feel like we're stationary, so the movement of the atmosphere makes it look like it's doing the moving, not that we're doing the moving. So especially in the equatorial region, the tropical region, that's where, as the Earth is spinning this way, the clouds seem to be moving eastward because they're sitting pretty much where they were. The Earth is just spinning under them. And Reuben got here. All right. Now, that's near the equatorial region, and the reason for that is the Earth is turning under them faster than they go. So generally, we have east to west flow near in the tropics. Okay, but the Earth does drag the atmosphere with it, and it's dragging the atmosphere this way, but it doesn't drag it as fast up here because the circle of the Earth is much smaller here than it is in the tropics. So now it's drugged the atmosphere, and now the atmosphere tends to be moving faster than the Earth is up here, so it goes mostly west to east. Not totally, but mostly west to east in the temperate region. I don't know what it does in the polar regions, okay? It probably is just a mess up there. And every now and then in the wintertime when we've got those Arctic vortexes, I think the spinning of the globe there just gets the air all mixed up, and if it starts heading south, whoa, those are cold and nasty times. We've had a couple in the last few years that have been bitterly cold. One about 3 or 4 years ago, we had pipes bursting and all sorts of things. It was really, really cold time. The last couple winters not had anything like that, but we have had a few. So the clouds get moved with the atmosphere. Different parts of the globe, they're getting moved in different directions and different speeds and things like this. So the transport through the atmosphere of those clouds. Now, some of those clouds will fill up, rain, and drop right back into the ocean. That's a pretty short circuit cycle there, okay? It comes out of the ocean and then cools and goes back into the ocean. However, many of the clouds make their way all the way over to land. Now, water, this is a term from the first half of the book that you don't have to know, but I'll try to explain it to you, has the highest specific heat of just about any substance on the planet. Okay? Water, the highest specific heat. That means it takes more heat to warm up, say, 1 gram of water, 1 degree Celsius, than it does any other thing. If you were to hold a piece of copper, fairly small piece of copper in your hand for very long, very soon it's the same temperature as your hand. Feels cool at first, but it comes rapidly. If you were to hold the same amount of water, if you could, in your hand, it's going to stay cooler longer because it takes more heat to warm up water than it does just about anything else. So, usually, if it's a warm time of year, the water, whatever time of year, it takes more heat to warm this. So it's quite often the case that this warm, moist air coming in here gets over land and has a different temperature regime. Now, especially if there's high elevations of land. And on the west coast, that's exactly what you have. You have this bed of mountains, the Sierra Nevadas down here, the Cascades up here, down in South America, you have the Andes along there. You just have these mountain ranges because of the Ring of Fire, remember? The subduction of the Pacific Plate and the Nazca Plate and other plates underneath the continental plates, and that has raised mountains, okay? So you tend to have elevation here. Well, the air, the moisture comes in, hits the mountains, and comes out then, okay? Sometimes it goes a ways before it hits the cooler, but it will, and as it then precipitates, that's when precipitation happens. The clouds dump the water back on the land. Now, when we talk about this, I already talked about it a little bit in the last chapter, we want the land to absorb as much water as possible, okay? For agricultural purposes, of course, okay? We'd like that to happen. We don't want it to wash away the soil. Bad news, erosion. We talked about that last chapter. But nevertheless, it will ultimately find its way back to the ocean. That's the cycle. The big cycle, okay? Condensation here, and precipitation, and then ultimately returns to the ocean. And there are many smaller subcycles here, like when the rain falls back in the ocean, that's a pretty short subcycle. Here, it could go onto the land, get absorbed into the land, and be there for a while before it ever makes its way back to the ocean. Or it could go into a lake or a large body of water, get it re-evaporated, and short cycle this way. But ultimately, the rivers take it back to the ocean, okay? With many possible subcycles in there, okay? That's what we mean by the hydrologic cycle. Now, let's go back to the clouds. The water evaporating off the ocean, okay, or any body of water, and going up into the air. The clouds form when the air masses are cooled to their dew point. Does anyone know what we mean by dew point? Any idea what? Probably have heard some of the weather people talk about dew points before. Do you know what that is?
The point where it absorbed. What is certain air absorbed more moisture than it could?
Okay, very good. Okay, Jordan, right? Okay. I think I got you in the right place. Okay, right on there. Okay. When water evaporates, it goes into the air and fills up spaces in between the air molecules. That's why you don't see it. Okay, it's just evaporating. Okay. At warmer temperatures, air can hold more and more liquid, more and more water, not liquid, gas, because the air molecules are further apart. They're more active, moving around faster and stuff. At warmer temperatures, things expand. At cooler temperatures, there's not as much energy, and there's not as much temperature. That's why it's cooler. And now the water starts coming out. Where it comes out, the temperature at which the moisture comes out of the air is the dew point. Okay, you're absolutely right. It's a temperature. When you have a whole lot of moisture in the air, the dew point, obviously, because you got that much, is pretty high because it's going to hold a lot until it starts coming out. But then in the wintertime, the dew point can be quite low because it just won't hold as much. But the clouds form when the air masses are cooled to the point. If those air masses carry lots of moisture up here, cooling as they go, they get closer and closer to what we call saturated. And then at some point, they won't hold anymore. That's the dew point, when it cools to that temperature. Generally, it's cooled by the upward movement of the air. That's called convection. We've talked about that before, too. Convection is when the warmer air being expanded because the molecules are moving, bouncing off each other faster, then it rises, the cooler air comes down. So that's convection, the carrying up of the warm, moist air. Now, and it can hit cool pockets of air in the atmosphere. That's one place, that's where the clouds form, okay? But they can also hit the barriers, such as we were talking about before, the mountain ranges, because those are at high elevations. And soil will typically can easily be at a cooler temperature than the water will be. We'll talk about this a little bit later too. And so that's why quite often, in fact, if you think about this, okay, what is one of the wettest cities in the U.S., or it's real famous for being lots of rainfall?
Washington.
New Orleans has a lot because it's right on the ocean. Seattle. There was jokes, I can't think what they call it, but they say that when they have the sighting of the sun, sometimes people just run out there just to see the sun because it's been cloudy for days and days and days. Maybe not raining the whole time, but just really overcast with cloud. Why is that? Because the Cascade Mountains are just inside, so all that Pacific moisture is coming in, getting blocked by the Cascades, so it's just, they've reached a dew point, and it's cooled by those barriers. What's on the other side of the Cascades and the Sierra Nevadas and certainly the Rocky Mountains? Pretty dry, because the mountains have blocked that moisture and kept it from moving inland. Okay? So the barriers are the mountain range. Now, the other things that cause the cooling is when you have colliding air masses with different densities. Have you heard the weather people talk about fronts? Cold fronts or warm fronts? Okay? Was it last week? We were just about every day right up around 98, 99 and stuff, and then finally toward the weekend, we had a couple mornings we could open our door because it was cooler outside than inside. A cool front had moved in. Not a cold front, a cool front. Yeah, those temperatures, anything better. And I mean, we were so happy it was in the lower 90s and upper 80s and felt like it was just freezing out at night. Because a cold front, a cool front, it technically was a cold front moved in. And so that's colliding air masses with different densities, different temperatures. Okay, that can also create the cooling. The cooling can come from natural convection going up into cooler ranges of the atmosphere, hitting a barrier, which is cooler, like mountain ranges, or hitting an air mass, which is cooler. So all those things can cool the air to the dew point and create the cloud forming process. The cloud formation depends on the atmospheric stability. Now, this topic, I find that they don't treat with they got it right, but they don't make it extraordinarily clear. But let's see if we can do a little bit of justice on it. Atmospheric stability. A stable atmosphere is one when you have a lifted parcel of air being cooler and denser than the surrounding air. I find that really sort of bizarre to talk about, because if it's being lifted, you would think, what is lifting it? If it's cooler and denser, it tends to go down, because that's what they say here, than the surrounding air. Well, that's a stable atmosphere because it's not going to force its way up. The lifted parcel returns to the original level because that's where it needs to go. It's lifted, but it's not going to create a problem going up. That's a stable atmosphere. I've actually heard Jerry Tracy refer to it this way, which I think is a closer description. He said, if y'all all know who Arnold Schwarzenegger is and was, he was in our generation. Jerry and I are fairly close to the same age. I don't think he's quite as old as I am, but we're in the same boat. Does anyone know who Arnold Schwarzenegger What? Tell me something about him.
Governor of California.
He was a governor of California. Before he was a governor of California, what was he? He was an actor, okay? Before he was an actor, does anyone know what he was? He was a weightlifter. You're absolutely right. Okay. Maya is here. Gotta find you. Sure, on the right block here. Now, time out for this moment. Maya, I was talking with Tamaya, okay? And she said you might be able to take some stuff to her. Is that right? Okay. So before you leave today, be sure you get the last 2 labs and the take-home test to take her. She was going to try to come today. She said she just walked out to have surgery. So here's how Jerry's at. Jerry, sort of average-sized guy, maybe a little smaller than most average Americans, but not by average. He said Arnold Schwarzenegger could lift him off back in his prime anyway, lift him and hold him probably fairly stably. Okay, he said, but if we reverse that and I tried to lift Arnold Schwarzenegger, that would not be a stable situation at all. So yeah, that's a little bit better way to look at it. If the lifted parcel of air is cooler or denser than the surrounding air, that's a stable situation because it's going to go back to its original level. Okay. An unstable atmosphere is when the lifted parcel of air is warmer and less dense than the surrounding air. So that means it's going to continue to drift upward. Okay? Move to a higher level, continuing to rise until it reaches the place where it starts falling. That upward draft of air is what makes things unstable. Okay? And these are sometimes called thermals. Now, that's a pretty single word bullet there, so they don't really say a lot with that. But when my wife's family used to take trips about every 3 or 4 years, they'd take a trip in the summer. And one time we went out to Jackson Hole, Wyoming, which is the Tetons, which are close to Yellowstone. We'd go to Yellowstone and come back, And these crazy people out there would be up on the Tetons and run off the side of the mountain with a set of sort of like a sail and ride the thermals. And not in the wildest imagination that I ever have any desire for that, but I can see a few hours going, hey! That's how pretty, and it really did look neat. But you could see them just ride the thermals. The upper draft of air kept the air under their sails, so to speak. Okay? So they rode the thermals. Lexi's here. Okay. If you've ever watched an eagle fly, do you ever see them flap their wings very much? No, they just fly. They ride the thermals. Now, we don't see many eagles where I'm from. Usually it's buzzards. But it doesn't sound as nice to say watch a buzzard fly. But if you're near the coast, watch the seagulls. They ride the thermals. Okay? Those are the upward draft of air, where the lifted parcel is warmer and it just keeps lifting. Okay? And sometimes those people on I guess they call them paragliders or parasails or something like that, they could stay up there, seem like for a very long period of time, riding those thermals. Okay. Now here's the illustration of it, and again, I don't find the picture and the description all that helpful, but here's what we've got. Here's the parcel of air. Now, this is a pretty good graph, but it just doesn't not explain well. You've got increasing temperatures going this way, Okay? So the parcel of air is here, and the temperature of the rising parcel of air is less than the temperature of the surrounding air. Okay? I would think this would, well, again, is not a great illustration. And this, if it's going anywhere, it's going to tend to come down. And that's stable. That's a stable situation. On the other hand, if the temperature of the rising parcel of air is greater than the temperature of the surrounding air, then you get the updraft. And those updrafts are what can create some of the instability. Okay? So that's my best way of looking at it. The updrafts are going to create the instability. Okay? Now, what you can do, and later we will be doing, picture this as the, this could be a cold front coming in here, and everything's fairly stable. Now, sometimes it won't be. And this could be more like a very, very warm situation. The warmer air hitting against the cooler and drifting up. Okay? Now that's not exactly what your fronts are, but you could almost tie them in that way. Okay. Just to keep you up with where we are, we just basically turned page 576 if you're following along in the book. And then they give an example here of one of those situations here. Parcel of air, and they give a volume and how much water, the mass of water contained in that. And then they go through all kinds of things, most of it referring to stuff in the first half of the book, which you haven't had, so that's why we don't do it. Specific heat of the air, specific heat of the water, and density, and all these kinds of things. It's not a bad idea to look through that, but it's a lot more involved there than what we have the background for, not having had the first half of the book. So we won't go into that, okay? But it is worth looking at the problem, okay? So here's the upward mobility of that warm, moist air. The rising moist air cools, eventually, no, okay, it's almost the same first line as the last one. Rising moist air cools, eventually reaches its dew point, and now the droplets begin to condense. Now, they have to have something to condense around, okay? And what those are called are condensation nuclei. Really a weird kind of thing. What in the world are these condensation nuclei? They can be a variety of things. It can be a dust particle, sometimes an ice crystal, okay? Something for that to attach to, okay? The droplets, these are the rising moist air, eventually reaches the dew point, so it wants to come out of the air. Okay, it needs something to attach to. Those are the condensation nuclei in that saturated air. If you have no condensation nuclei available or insufficient, your air gets what we call supersaturated. Okay, that means there's really more moisture there than the air can support. That's not a very stable situation either. Okay, but the cooling of that rising air is slowed by the release of the latent heat of vaporization. Again, this is coming from the first half of the book. Let me try to explain to you what they mean by that. Okay. When something heats up, there can be two responses to that material. Okay? Number one, it gets hotter. Okay? That's called sensible heat. You sense that change of temperature. Okay? However, when you are at the point say, of boiling water. Let's start there. You can put that water in the pot on the stove, and the water is probably going to be pretty close to air temperature when you put it in there. You turn on the heat, and the water starts heating up. That's sensible heat. It changes its temperature. Okay? Then it keeps increasing until it reaches the boiling point. And at the boiling point, it doesn't change temperature anymore. It changes its phase. Some people say state. It changes from a liquid to a gas. Okay? That change of phase is called vaporization. You're adding heat, but you're not changing the temperature. You're adding latent heat. And the word latent means hidden. Hidden heat. Okay? Hopefully none of you will ever be scalded by steam. But if you are ever scalded by steam, you will certainly know it, because that's a worse burn than a heat burn, you might say. Because the steam has latent heat. It hasn't just got the heat of the sensible heat, 100 degrees Celsius, 212 Fahrenheit. That's enough to burn you, but it also has that latent heat, the hidden heat of vaporization. Now, it happens also on the lower end, too. Have you ever picked up an ice cube out of the freezer, but you had just a little bit of moisture on your hand? What happens? It sticks to you. Why does it stick to you? Because that ice cube is below the freezing point of water. The freezer has probably got it down like minus 10, 12, 15 Celsius, which would be probably down in the 20s or so, or even below that Fahrenheit. So it's below the freezing point of water. So if you have that little bit of water on your hand, you reach down and touch the ice cube, it doesn't start melting, it freezes the water on your hand. And that's why it sticks to you. And your hand is always a little moist, so it sticks to you because it's frozen there. You're below the heat of freezing. And that kind of a freezer burn can really be painful too. Frostbite, we call it. Okay, it can be called. Okay, so when the cooling of the rising air, the water goes out of being a gas into a liquid. Now it releases some of that heat of vaporization, the latent heat of vaporization, and that slows the cooling. Okay? It was cooling as it rose. Now it slows because it's releasing that stored heat of vaporization. Now, huge number of droplets that this is happening to, that forms the clouds. The little white things we see out there. Puffy, beautiful white things we see out there. That's what makes a cloud. The upward movement of the moist air coming off the oceans or wherever, and when they reach their dew point, they start condensing around those condensation nuclei, and then they start coalescing those drops together and forming droplets of clouds. Okay. Now we get to precipitation part. What precipitation is, water returning to the Earth's surface. Okay? Dew and frost are not precipitation, they're surface processes. You have moist air near the surface of the Earth. Overnight the temperature drops further. Now it can't hold that, but it's not the air up here, it's the air right at the surface, and the air near the surface drops the water out, probably on leaves, on sticks, on things like this, and that's why dew covers things on the surface. It doesn't fall out of the air, it's a surface phenomenon. In the wintertime, that's frost, okay? Doing that. If you're below freezing, it comes out as frost, not dew, okay? Same type thing, only it's frozen. Precipitation forms two ways. One way is those water droplets that are up there, they keep coalescing into bigger droplets and stuff until they get so heavy they fall. The coalescence of the cloud droplets. But really, most of it, believe it or not, comes from the growth of ice crystals. Because way up there, the air is really, really cold. Look at most of the mountains. The really tall mountains. Now, none of them we have around here. Oak Mountain, Red Mountain. Sorry, but they're not really mountains. I mean, they're barely hills. I mean, go out west. Mount Rainier, near Washington, Seattle. Most of those other mountains, remember we've seen them? The upper part is white. It's covered with snow. Even, we were talking about last time, Mount Kilimanjaro, near the equator, used to be covered with snow. The snow of Kilimanjaro, one of Ernest Hemingway's novels. I think it was a novel or a novelette. Okay? But it was, at high temperatures, at high elevations, it's very, very cold. So the water droplets up there are not water droplets, they're ice crystals. And those can form your condensation nuclei, and the growth of those ice crystals, they get so heavy, they fall out of the sky. Now, if they make it to the ground, what do we call that? Snow. No, not snow. Snow cools as droplets.
Hail?
Hail, exactly. If they coalesce in growth, they can be hail. Now, snow is ice crystals, but they're usually individual or very small droplets that have changed. But in the summertime, when the ice falls out of the sky, that's hail. Okay? And around here, it's more likely to be hail than it is snow. Growth of the ice crystals. Because on their way down, they encounter the warmer regions of the atmosphere and they melt. Okay? And some of those, those summer storms, I can remember, I don't know why, but traveling to North Carolina to see the grandparents, my father driving us up there, every now and then we'd hit one of those summer storms, and those first few drops that hit the windshield, they just almost exploded on the windowsill. They were huge. Those had been ice crystals. They would have been a hailstone had they been closer, but they fell as that because it was just big old drops. They were melted ice crystals. Now, going back to this coalescence process, it takes place in the warm cumulus clouds near the tropic oceans. Here, okay, in the tropics, between the Tropic of Cancer and the Tropic of Capricorn, in there, in the ocean, Pacific, the Atlantic, in that region, the Indian, those places, warm cumulus cloud near the tropic oceans, that's when the coalescence of droplets. Most of the stuff we get really was ice crystals, okay? The clouds contain, especially over the ocean, they say giant salt condensation nuclei. They're not really all that big, but they're bigger than microscopic, okay? It's not big chunks of salt flying around up there. It's just those nuclei are there and they start forming. It's over the ocean. Some of the salt is being carried up in the evaporation process. The ice crystal process, the second one over there, this takes place in clouds at the middle of the ocean. That's where we live, okay? Most of our storms, even in the summertime, they're coming from the ice crystals, okay? The ice crystals capture nearby water molecules. They grow bigger and bigger and bigger until they're so heavy they fall out, okay? Now, you're right when you said snow in the wintertime, they don't have to get all that big. They are going to fall out pretty quickly. Well, that's going to be near the surface. It's going to be cold like that. But in the summertime, if they're way up there, they've gotten quite heavy, falling down, they melt on the way down. They melt and turn to rain in the summertime. Snow in the winter. rain in the summer, but if any of them make it down in the summer, that's called hail. Okay? Because the hail isn't that nice little floating crystals of ice that snow is. They're big old chunks of ice that came from way, way up there, where they captured the water molecules and kept getting bigger and bigger and bigger. Now, I really don't care for the organization of this all that much, because they're now going to talk about the weather producers, which are great topics and stuff, but then we're going to come back to talking about the fronts and stuff. I guess maybe this is the best way to do it, but it seems like it's a little disjointed to me. But I guess doing it the other way would seem disjointed the other way. Okay. Here's the idealized model. Okay. Now, again, get your globe. The good old handy-dandy visual aid here. The region between 10 degrees north and 10 degrees south of the equator, it receives the most direct solar radiation. Okay? A couple reasons for this. Number one, it's closer to the sun. Here, we're further from the sun. Here, we're closer. Even when we're tilted away from the sun, this gets more direct radiation. Now, the second reason is, besides it bulging out here being closer to the sun, if you think about it, the radiation from the sun goes through less atmosphere here than it does here. Because here it's going to see the atmosphere like this. It's cutting across, going through a lot of atmosphere before it reaches the surface. Here, just going straight through. The shortest distance to it. So, the region between 10 degrees north, 10 degrees south receives more direct solar energy from the sun. The air heats up and rises. Okay, and the air heats up and rises. Well, where's it got to go? It either goes north or south, toward the pole. Now, it doesn't go directly toward the pole, but it goes in that direction. Okay. Now, the air cools as it gets away from the equator, equatorial region, and becomes more dense as it rises. Okay, as it's cooling, I would say as it's cooling. Okay, and now it starts sinking back to the surface. Now, where does it come back? Well, outside of the tropics, but not too far outside, around 30 degrees north and 30 degrees south. Now, I didn't realize this until I started teaching this course, because I would have told you, if you'd have asked me back then what our normal atmospheric pressure was, I would say a little bit below what we, 1 atmosphere. And why? Well, we're inland. Birmingham is what? About 300 or 400 miles from the coast? Is that about right? That far? I think so. Something about like that. And we're going up in elevation. I mean, Red Mountain, we're going up in elevation. So I would think we'd be a little bit less than 1 atmosphere of pressure. 1 atmosphere of pressure to me would be at sea level, where you have the whole atmosphere above. Okay? Now, we're not at huge elevation, if I were to guess it. But in every lab that we did, when we were doing a temperature lab, we would always look up and see what the barometric pressure was. And the majority of the time, it was just a little bit above 1 atmosphere of pressure. Why is this? Well, guess where we are? 33 degrees north. 23 minutes and 45 seconds. But yeah, we're right in that region where the air cools and comes back down. We're in that high pressure band. Actually, the equator, even on the ocean, is in a low pressure band because the air is rising there because of the heat. Coming up, going north and south, and then coming back down around here. So we are just about always slightly above 1 atmosphere of pressure. What's the end result of this? You have a band of low pressure near the equator and bands of higher pressure, 30 degrees north and 30 degrees south. Now, where does most weather situations come from? High pressures or low pressures? Look, what is a hurricane? Very low. The higher the category of hurricane, the lower the pressure is at its center. When we're in a high pressure situation, hardly any clouds, hardly anything, very little chance for precipitation. In fact, these last several weeks, I've been wondering, I can remember back when I was on the farm, we talked about a Bermuda high. If we ever got into a Bermuda high, that would influence, we were over in Georgia, that just kept us dry. Going the wrong way. No, that's exactly how the airflow would be around the Bermuda high. It would keep you dry because it was high pressure. So we tend to be in an area that, if it weren't for the Gulf of Mexico, we would really be dry. So we'll talk about that a little bit later. So large convective cells form to equalize those pressures. Well, when you have low pressure here, high pressure here, something has to equalize it. And when you saw those clouds and movement in the Gulf of Mexico, that's typically what it is. Now, in the summertime like we're in now, what just hit Houston? Not Houston, Alabama, Houston, Texas. Say again? A pretty big tropical depression. Dumped almost as much rain on the Houston area as hurricane, what was the one a few years ago? Harvey, is that it? Yeah. This is just a tropical depression, maybe a tropical storm, I don't know, but just dumped the rain on them. Okay? It was so sad. Some people had just rebuilt from Harvey, and the whole place flooded. And have to start wondering, there's somewhere else we need to go, you know. So these large convective cells form to equalize the pressures. Some of those can be let's just call them cyclonic. Okay, we'll get to that a little bit later. So, one of the weather producers is called your air masses. These are large, horizontally uniform bodies of air. So, like this, there's not much variation in them. Large, horizontally uniform bodies of air. The moisture and temperature conditions are almost the same within that whole block of air. Okay? There are four main types. There's smaller types. So let's talk about the four main types. First, you have the continental polar. Okay, for us, that would be air masses coming down out of Canada. They're coming from the polar regions over the land masses. Now, land masses tend to be drier, but tend to probably colder. Remember, the water has the highest specific heat, soil much lower specific heat. So these continental polars are cold, typically dry air masses coming down. The maritime polar, now, any of you ever traveled in the far northeast of the U.S., Boston, Maine, you know, any of those areas up there? What they fear more than about anything else is a nor'easter. They don't know how to talk well up there. They say nor'easter, coming from the northeast. Okay? These are maritime polar air masses. Cold, but wet. Oh, those can cause some problems. Okay? Then we have the continental tropical. Okay? For us, think the air coming off of Mexico. Continental, coming off the continental, goodness gracious. We talked about the last couple. Plates, continental plates, where it's above the plate. coming off of that, think Mexico, and blowing in. Those are hot and dry. Where are our major deserts? The Mojave Desert. New Mexico has desert. Arizona has desert. West Texas desert. That's what causes that. The continental tropical. And then we have the maritime tropical. Oh, thank you, Gulf of Mexico. That's what we get. Warm, but generally moist. Very moist. That's why we're not the desert they are there, because this is our air mass producer, the Gulf of Mexico. Sure, in the wintertime, we dread those coming out of Canada. The continental polar. We don't want to see them. Those are cold and miserable. But most of the time, we've got those maritime tropical coming up. And we may get tired of the rain, but rain is good, in my book anyway. These dictate the air mass weather, the big systems caused by these various air masses. Weather conditions remain the same over several days because these are huge air masses, and it'll be the same. We are right now in some major air mass. I don't know what's causing this, but we have been so hot and so dry for so long. I mean, we're nearing the end of September, and I believe we've had more 90-plus degree days in the month of September than I can remember some summers in the past. When we've had just a nice, fairly pleasant summer, and a hot day would be in the upper 80s. We've had more 90-plus degree days in September than I can remember in a few summers. Not that many, not very recently, but way back. And our weather conditions, I hear them say, and the temperature today will be in the upper 90s with the lows and and tomorrow will be in the upper 90s with the lows, and then the next week will be in the upper 90s. Same thing, same verse, second verse, same as the first, over and over, several day periods. We've got to be in air mass weather right now, okay? The weather changes when a new air mass moves in, or when the air mass acquires the local conditions and we get back to normal. It's not going to happen, like the pleasant temperatures. Boy, we were, wasn't it last week, early part of the week, 99, 98, just about every day. Pretty miserable, I think. If it had been a lot more humid than what it was, it would have been totally unbearable, but it was relatively dry, which of course is contributing to drought. Now, this is showing what I was kind of pointing out in the globe. The continental polar air masses, basically those coming down out of Canada. Off the continental areas, Canada, land, and they're coming from the north, continental polar. And if you ever, they used to do this a lot more on the weather than I hear them do now. Of course, I don't listen. We don't watch much TV anymore. But I can remember when I was younger, they used to always say where the coldest place in the U.S. was that day. And so many times it wasn't Maine. It was right in here. It was Minnesota, maybe North Dakota, upper Michigan, somewhere right in here was the coldest spot that day. In the continental U.S. anyway. Not over here and not over here, because the continental polar just tended to be so much colder. The hottest regions were usually down here in the continental tropical. Arizona, New Mexico, Texas, Southern California, just really, really hot. Okay? Dry heat, but hot. Then your maritime polar, like I said, the nor'easters coming off the North Atlantic here, or the maritime polar keeping Washington State, Seattle, Portland, Oregon, these areas just hung over with clouds, almost always. The maritime tropical some in the eastern part of the U.S. It's not quite so common here because your prevalent airflow is west to east in the temperate regions where we are, so you don't get that much. But occasionally you do get maritime tropical, I would say tropical maritime coming in here. That's usually when it's hurricane season. That's when you get much. Here, though, it's almost always maritime tropical. Gulf of Mexico, keeping us warm, but keeping us moist most of the time. And as you said, Louisiana, New Orleans, yeah, it's always wet. Okay, a little bit of maritime tropical over here in the Pacific Southwest, but not so much. I mean, even San Diego, further south you can get in the Southwest, just above the Mexico, it's not nearly as wet as we are over here. In fact, the beaches, when you see people going to the beach in Southern California, quite often it's in wetsuits. Because, we'll talk about this next time, the ocean currents are coming this way. So you get polar type water is coming down here, keeping this whole area cool. So this is minimal here compared to what we've got here. Now, your figure in your book, I like better than this one. I didn't point out when we were there. I probably should have. On page 577, boy, what a picture of a thunderstorm coming in. Precipitation, that rain is those dark clouds, really dense, blocking the sun, and the rain just starts falling out of it. Your figure in the book, they have just little bitty bubbles here. I like yours a lot better. Continental polar, that's a lot more descriptive to me. Maritime polar coming in like that, maritime polar like this. Maritime tropical, big air mass here, but just a little bit comes in. Maritime tropical over here, especially at the Gulf of Mexico. But the continental tropical off Mexico here, yeah, that I like better than that. Okay, so pay attention to your book. Nothing replaces reading the book, remember? Okay. And by the way, the figure on the next page, 579, very similar to the shot that we saw at the very first slide. Only this is a different day and the cloud formations are different, but there's Cuba and Florida and the Gulf of Mexico, the whole works there. Okay. Now, this then leads to the weather fronts. These are the boundaries between these big air masses. Okay? So, seems like it's been a long time since we've had a boundary come through. We seem to be just sitting in the middle of the air mass. Okay, but the boundaries are when you have the changes. Because the boundaries between the air masses of different temperatures, you either have cold air moving in against hot air, or you have hot air coming up against cold air. Now, occasionally you'll have other variations on it. If it's hot, dry air coming against cold air, you just have a big change of temperature. Cold air moving against warm, moist air, then you're going to have some precipitation. So let's talk first about the situation where you have the cold front moving in, the cold air mass moves in into and displaces a warmer air upward. Okay. Now this is that situation where the cold air moves in, forcing the warm air up. Okay? This is that unstable situation. The cold air moves in, forcing the warm air up. The warm air is now less dense than the colder air that's surrounding it. That's when you have an unstable situation. The moist rising air is cooled, leading to large cumulus clouds, and these are often thunderstorm clouds. Okay? On the other hand, the warm front moving in, pushing out the cold air, it advances over the cooler air masses. Now, it almost sounds like the same thing, except that it's the invader now, and it moves up, and the prevalent air, the cooler air is now underneath the warmer air that's surrounding it. That's a stable situation. Pretty stable, anyway. Now, let's get a picture of how that looks. Well, first they do so this to me almost seems a little out of order here, but let's hit it while it's here. And it seems like they could have had a map that was a little more descriptive than this one, but this one's not too bad. All right, if you can figure out what it is. This is a high pressure system. Now again, just like we had with our topographic maps, remember we called those contour lines, those were lines of equal elevation, isoclines, okay? The lines on this map are isobars, equal barometric pressure. And they don't, or at least I can't read it. Here are the numbers that are on those things, and this is a high here. This, the highest numbers you have, they're increasing from here to here, increasing from here to here. So this is your high goodness gracious, just a high pressure area. Okay, let's just call it that. Now, get this. The high pressure area, the winds tend to turn clockwise. Okay, just for your reference. But there's very little moisture here. Well, look at it. It's probably being caused by continental, tropical air coming in here. Very dry air. This is a very dry area. High pressure, you're not going to have any rain anytime soon. Followed by another high pressure here. Okay? But as your pressures drop off, going this way, you're getting into lower pressures here. Again, not a lot happening here. Here's another high up here, another high here. There's just not a lot of activity this day. They're showing here until you get over here. There's a low pressure area. Here we have Tegan, okay. I thought it looked like you from the back, but I couldn't tell. And Ethan, is that right? No. Okay. Yeah, I thought so. Well, I was finding you is what I was doing. Ethan and Tegan, you come in alpha or in rhymes anyway. Okay. All right. Good deal. Anyone else come in that I didn't see when you came in? Okay. All right. But up here we have a low pressure area. Okay. Around low pressure areas, the winds go counterclockwise. Okay. This is that nor'easter I was talking about, because it brings that cold, wet air down against the shore here. That's what they dread. Boy, the sailors, the people who went out on the sailing ship, the fishermen and stuff like this, that's not what they want to run into in the Northeast. It's like it. Now here's another thing. Notice how close these isobars are. Okay? What did it mean when the isoclines were real close together? Remember that last topographic map when the lines were real close together? Very steep slope. Okay? So what does it mean for the pressure lines to be close together? That means you have rapidly changing pressure. Where you have rapidly changing pressure, you have big winds. So therefore, you're going to have very windy, stormy conditions right there. Here where the lines are way far apart, you probably have hardly a breath of a breeze there. There's nothing to drive the wind, because they're all at the same pressure, so everything's just hunky-dory staying right there. And it's hot. I don't think I want to be there that day, okay? No wind to cool you off up here. I don't want to be there that day. It's a cold, fierce wind blowing there. Okay? There's the only low that I see on the map. And that's a major one because you see, even these highs, the lines are really well spaced between each other, so there's not a lot of wind. But here, enormous, very rapid wind, especially through there. Okay? Because the lines, the isobars are very close together. That's jumping ahead of what we need to hear. But let's see if we can get the current slide. Here we go. Here is the cold front. The cold air mass moving in. Now this is the side shot. This is the overhead shot. Okay? The front's coming in. The cold air forces the warm air that was there up and above. Warm, moist air going above cold air. Unstable situation. Okay? Later you'll see a slide that illustrates better that. Okay? From the top, this doesn't show a whole lot, except you're looking down at the town now, and there's your front moving in this way. Now, in the wintertime when you have those, you'll sometimes see on the weather map, this is here in the southeast, maybe 60s on this side of it, and 30s and 40s on that side, in a very short distance. If you have a temperature gradient like that, you're going to have some winds from that too. In fact, when you have the tornadic weather, you quite often have a cold air mass moving in against warm, moist, and you can have some major issues going on there. We'll be talking about those later. This is your cold front. Cold air mass stays right near the surface of the earth, forcing the warm, moist air above it. You're going to get, the odds are you're going to get rain from that. Okay? Why is it not showing anything here? Okay. There was supposed to be in here a warm front. The slide's not showing up. Where the warm front's moving in, it's not as abrupt here. It's a very slanted, gradual increase. The warm air basically, it almost turns it around and it moves up over the cold air like this. Not nearly as abrupt as this is. If you look in your book, you'll see that. That's on page, no, maybe not. Oh, no, it's coming up. I'm sorry. These are the ones I was looking for anyway. Okay, there again is the cold front. Okay? Where the cold front's moving in, cold, dense air is moving here, forcing the warm air up. When you force that warm, moist air up, now you get your condensation into clouds, and boy, do these form the clouds. Now, I don't know if you can tell this. Here's the altitude over here in kilometers. Okay? 10 kilometers is about 6 miles. This is 15 kilometers, which would be $90 or so miles up. I mean, that's not right. 9, okay. Yeah, 9 miles. About 9 miles up. 9 miles up, cloud? Yeah, that's a monster of a cloud. And this is what's typically formed when you have a major cold front hitting warm, moist air. Okay? Talk about unstable. This is unstable. Here you have the rain leading the front and with the front. Okay? If this was coming in too rapidly, you could actually have tornadic activity. Because the air is moving up, you create a low pressure. That low pressure creates the turbulent flow, and you could have some pretty major tornadic activity coming out of this. It can happen. Now here's the other thing, that moist air being sucked up here, into here. What is it up here about 9 miles up? Cold, really, really cold. Ice crystals like crazy up here. This is where this warm, moist air is coming up, being sucked up into this, forming ice. Now, the ice crystals are big enough they want to fall, but the airflow is up, forcing them back up. It's kind of like, second?
Like Powerball?
Yeah, something like that. Yeah, just do it up. I was sort of thinking of a popcorn popper. You know, it wants to fall down, but it keeps getting pushed further back up. So that's why it keeps cycling, and as ice crystals move back up and get bigger and heavier, come back up, move up. We'll see that in just a few minutes. They're going to do a lot better job of that later. But that's what's happening when the cold front comes in against hot, warm air. Moist air. Warm, moist air. Okay? Here is your warm front. This is what I said. It's going in the other direction. The warm air is coming in against the cold air that was in place, so it's going up like this, and you see it's a fairly stable situation. This air is being lifted, but it's colder than what the air coming in here is, so this is a fairly stable situation. Yeah, you'll get some rainfall out of this, and you'll get cumulus clouds. But look at those sizes. Maybe 4 kilometers up, that would be 2.4 miles as opposed to 9 miles, okay? Yeah, big difference here. Yeah, you get rain. Nice, slow, gentle rain, okay? Nothing bad, just the type of rainfall you like. Not going to wash away anything, okay? The airflow is like this. So there is your warm front coming against cold air. Cold front going against warm air, unstable, generally. Okay, any questions? All right. Now, before I go too much further, and by the way, the figure that we were looking at earlier of the weather map, they do sort of a made-up weather map here, but at least it shows you a lot more information here. How the isobars are increasing in number going around the high, decreasing in number coming around the low. These are your, what we were calling contour intervals. These are your barometric pressure intervals. There will be about 4, and let's see what these are measured at. These are probably measured in millibars or torrs. I can't tell which looking at them. They're very close to the same measure, either millibars or torrs, or what those numbers are. They don't tell you that here, but that's your interval. All right, now this next one, blurb here, now this is a break from the action here, the urban heat islands. Have any of you heard of those before? Okay. We have them here, okay? I notice this especially in the wintertime. I can leave here, like the last part of this term, second mini-term, I'll be teaching Physical Science 2 at a later time. We'll be getting out of here about, unless I can get to talk to students into moving it up some, about 7:45 rather than 5:45, okay? You talk about making the wife mad, that's, okay. I get home pretty late, and it's getting dark sooner. It's cooling off, and when I'm going home, I'll get in a vehicle, and I have a little thermometer thing in there. It shows the temperature on my dashboard, and I'll see what it is. And let's just say it's 40 degrees. That's a bit cold for December, but let's just use 40. And I'll get on the expressway and start heading up. And as I get away from Bessemer, I'll actually see the temperature start going down. But I don't know if that's because I'm leaving Bessemer or because I'm going northeast. Now going north, it's not going very far north, but some north. You would think it would get cooler. Going east, where the sun's been down a little longer, you would think it would be getting cooler. And, so it should be getting, and it's getting later in the night as I'm driving home. So you would think the temperature would be dropping, right? And it does for a while until I get about halfway between here and Fairfield, around Fairfield or so. And somewhere there, the temperature starts going up again. Slowly, but it does. But you're hitting more city-like thing. When I get close to Birmingham, temperature gets hotter than it was when I left here. That's the urban heat island effect. Because an urban area, you have lots of concrete, lots of pavement, asphalt, parking lots, fewer trees, buildings, and more cars, more energy being escaping from the buildings that you have there and stuff. Out in the wooded areas and stuff, it's not going to be the same, okay? That's what it's talking about, urban heat island. We'll come back and look at that. That could be a paper topic if someone's interested in looking into that. This has a little bit of discussion question, but that's a possibility there too. Now, one thing that the slideshow left off is your stationary front, okay? And that's one where the two air masses sort of battle and neither wins. So it's not a warm or a cold front, it's stationary. And they just sit there, and sometimes those can be weather producers themselves. If this warm air is moist and the cold air is pretty cold, you could just be drenched on the front, dry on either side of it, but on the front, and it just sits there. And it sits there, and that same area just gets more and more rain. That has happened occasionally. I can remember a few, none too recently that I recall. Okay. Now, on page 582, we're moving into waves and cyclones. Now, I had not heard of a tropical wave. I couldn't remember ever hearing of it until, and this was before I started working here, I was working at Southern Research Institute in Southside Birmingham, and we were on a radon project, and our radon project was centered around Polk County, Florida, Lakeland, Bartow, those areas down there. They do a lot of phosphate mining there, and when they bring up that phosphate, it tends to have small traces of uranium in it, not enough to be set off Geiger counters or anything, but more than normal, okay? Well, they extract the phosphate rock and concentrate that stuff that's left over, which includes some of the uranium stuff. So some of the waste product from that can have even higher uranium and radium content than you would expect anywhere else. So we were studying radon, because that's the chain that radon comes from, down here. And we had built a test facility, actually another group that built it, and we were running the experiments on it. And we were doing just all sorts of measurements in and out of the building and around like this, well insulated, stuff like this, and we were watching the data. Our engineer on the site would collect the data and send them to us in files, and I was sort of doing the analysis of that. And one day, the radon just would, and just peaked. And we looked at other things like barometric pressure and stuff. Barometric pressure had just dropped like crazy. And I said, what in the world is going on here? And I called Jerry Tracy, because I knew him at the Weather Center, and said, what could have caused this big a drop of pressure? That's obviously what's sucking the radon into the building. And he said, down in that area could easily have been a tropical wave. Now, said not often do you get the tropical maritime coming off the Atlantic because the prevalent winds are west to east in the temperate regions where we live. But occasionally you'll get one of those waves that comes in, and that could be associated with a hurricane or not quite, just a tropical system like that, and you get those tropical waves. So that's one thing. My first encounter with a wave, this was a tropical wave. Waves can lead to cyclones, and cyclones are also what we call tornadoes, okay? But they could be bigger and they could be hurricanes. But let's get to it. What's the mechanism here? The bulges or the waves often form between oppositely moving air masses. So maybe you have a hot air mass coming in like this, but a cold air mass coming here, and you have a difference in directions of them. Well, that can create the cold air masses tend to be higher pressure, the warm air masses lower pressure, so you have pressure bulges, you have temperature bulges, you might say. The overriding uplifted cold air produces, now they're going to show, here again is a graphic that I find a little less than satisfied, okay? But here you have a situation that obviously to me is not stable, okay? I don't know why they have the warm air down here and the cold air up there. That's backwards. Cold air is usually denser, warm air isn't, but you have the oppositely moving masses, and maybe the warm air was there first and the cold air has moved over it. It's not a good situation, okay? So what happens is the warm air tries to rise under it. Now, I can't justify their pictures here. The cold air tries to come down under it. So what we have here is a cold front on this side, because the cold air is moving this way, the warm air this way, opposite moving air. That's what it says, between opposite moving air masses. And this is the cold front. This would be the warm front over here. As the warm air is trying to move up, the cold air is trying to force its way down. Okay? So you get these bulges in pressure and other measures. Okay? Well, if this continues to form, the cold air pushing down here, the warm air here, you get a very low pressure area here. The warm air is coming up under this, the cold air is moving around like this, and because it's moving faster, it tends to lower the pressure, and so you have a low pressure center right here. Okay. Then they throw in this term that they don't define at all, an occluded front. Okay? And they don't describe what it is. This figure does almost nothing for me. It's sort of like this collapses on itself, is the best I can figure. But again, it doesn't, they don't describe it well at all. But then what comes out of this is your circulation of air. Okay? What that can be or can become is a cyclone. That's on a big enough scale, it's just a low pressure cell. Okay? And that could create, moisture and some storms and things like this. But if it's a tight enough one, then you could have tornadic activity. And that is what ultimately is going to be called the cyclone. Okay? The overriding uplifted cold air produces a low pressure. That's what this figure shows. The further cold front motion leads to an occluded front, which is here, and the cyclonic storm. Okay. Remember, was it April 2011? Okay. That must have been one of these things in space. Okay. It was just all up and down the coast of Alabama is where it came in. It was just incredible. These things were popping up, really tight storm, all up and down. I mean, there were, at one time it seemed like on the screen 3 to 5, 4 to 5 tornadoes, all at the same time, you know, on the same screen of the state all the time. And it was just unbelievable. They just said, we can't worry about these. We're going to just focus on these here, you know. Usually if there was one tornado in the area, everybody's focused on that and talking about it. They had so many, they only would say, well, let's just get the biggest one closest to us, you know, and not worry about the others. Okay. Amazing. And that's what forms a cyclone. A low pressure area with inflowing upward force winds. That's what creates the low pressure. The circulation pattern caused by the good old Coriolis effect. Remember that? When you have upward movement and the spinning of the earth, you get that spin like that. And low pressure is in the northern hemisphere is always counterclockwise. High pressure clockwise, low pressure counterclockwise. You go to the southern hemisphere and everything is reversed. High pressure is counterclockwise, low pressure is clockwise. Just because the spin is different. The torque is different. I've told you about my physics professor who ran to the bathroom to flush the toilet in Rio just to see it flow the opposite direction. Yeah, right. Okay. An anticyclone is in a high pressure area where the flow is clockwise. The air sinks, is warmed, and relative humidity is lowered because the cold air is coming down and dropping the humidity. Okay. Make sense? What's that? Right. I'm all in favor. Okay, let's see where we are here. Okay. We'll start with that next slide, which is a pretty good one. I want to talk about it. I was going to say, so I meant to earlier, for my voice, I went to the UAB game on Saturday, so yelled too much. Sorry about that. Okay. I think we hit this slide pretty well, but the one that followed it, the reason we're still here, is this one. It seems, and people will say this isn't the case, but it does seem that the cyclonic patterns do follow pretty much paths, okay? For the longest time, the biggest seemed like they were usually through here, Oklahoma, Kansas, some of these areas. These were the predominant routes. But it seems like lately you get more and more that come like this. April 2011, this was pretty much the route it followed. Okay. Now, it didn't continue being tornadoes. Well, actually, I think they did have tornadoes, not nearly as many as we did, but they did have tornadic activity carried up into the northeast. So they do tend to follow fairly regular kind of patterns. And sad, but true. And you can, and what time of year was it? Spring, when things are changing. You've had the cold of winter, now you get the warming of spring, you get the changes, you get the air masses flowing past each other, getting inverted, that kind of stuff, and that's when problems occur. And boy, did they ever. I mean, this was pretty much the center of that. It went all up and down, the whole line of the state, but it centered right along that path and moved on. So not a bad representation there. All right. Now we move into major storms. This is on page 582 is where that picks up. And when we're saying major storms, this isn't just a rainstorm or a little thunderstorm, the big thunderstorms, yes. It's a rapid, violent weather change. And again, where you've had cool temperatures and suddenly warmer, more likely warm temperatures and suddenly cold. Those are the ones that tend to cause it. So rapid, violent weather changes, often associated with a frontal passage. And this is what you see happening. And I wanted Jerry to go into this, I like for students to ask the questions and him to talk about whatever he wants to talk about. But what is it that makes what they call the hook echoes and things like this? This is where you hear them talk about that when it's that kind of weather going on. But it is a frontal passage, usually a cold front pushing against existing warm, moist air. Now, there's three major types of these, and these are in increasing order of total energy, but thunderstorms, they can be major, period. Tornadoes, that's generally worse than a thunderstorm. The thunderstorm usually going to cover a bigger area. Tornadoes very specific. Then hurricanes, huge, massive, okay? Not as intense as a tornado, but covering a lot bigger area. That's the most energy. So we'll hit them in that order. So let's start with thunderstorms. Okay? Usually develop in warm, very moist, unstable air. Okay? That's where it occurs. So when you have that hot, humid air so thick you could feel like you could cut it with a knife, if you have any changes happening, it could get violent really quickly. 3 stages. First, they call the cumulus stage. It's associated with convection, and these are those 3 things we mentioned before. Convection, mountain barriers, or cold fronts. Anytime that warm, very moist, unstable air hits something, either from convection, a mountain barrier, or hits another cold air mass. That's what this is talking about. This is where the clouds start forming. That warm, moist air gets sucked up into what's going to be a cumulus cloud. It's a forming cumulus cloud. You have upward flow of the warm, moist air. Of course, the upward flow of warm, moist air is unstable because it's getting cooler up here and things are going to start happening. Okay? Now, that's the cumulus phase, the first stage. Then you get to the mature stage. Here, the updraft can no longer support the growing ice crystals because this is warm, moist air coming up, and that warm, moist air going higher and higher in elevation, it's getting cooler and cooler, so ice crystals start forming in here. And the ice crystals get bigger and bigger because more warm, moist air comes up, hits them. They become the nuclei, the condensation nuclei, and they're growing and growing. The updraft can no longer support those growing ice crystals, so now things start falling down. Okay? Ice crystals and snowflakes. This could be a snowstorm in the wintertime. Was anyone, I have a hard time judging your ages. In 93, y'all were all alive, weren't you? No, not yet. Okay. Y'all probably, yeah, a few of us were. Okay. Anyone remember what happened in the winter of 93? In March of 93, in fact. What's that?
Was there snow?
Yes. Was it ever snow? Something like 13 to 14 inches of snow in March. Not in the dead of winter. It was awful. In fact, the emergency vehicles were running off the road. The ambulances could not get to hospitals. Okay? They were running off the road. I don't know how it happened. We kept power the whole time. It was bitterly cold and miserable conditions, but our power never went off. So we could go out and play in the snow and get really cold, come into a warm house, watch the TV, everybody else's misery, you know. It was terrible. But I remember seeing 4 guys carrying a pregnant woman up the hill to Brookwood Hospital because there was not a vehicle anywhere that could make it up the hill. they carried her up to her emergency room, delivery room, whatever, because a vehicle could not make it up there. Ambulances couldn't, police cars couldn't, nothing could make it up there. It was an incredible time. So this can happen at any time of year. Most of the time it's happening in the summertime, but it can happen anytime. So it could be snow. So when it says ice crystals and snowflakes, it can be snow. Okay? The falling frozen water melts and becomes rain as it comes back down here. Up here at 10 kilometers, at 6 miles up, that's ice, okay? But as it comes down, it's hitting warm, moist air coming up still, and it melts, and that's rain. And it can be pretty violent rain, too, okay? If they're tall enough and heavy enough, and there's enough updraft, keeping them back, they're growing bigger and bigger, some of that actually comes out as hail. So hail can form in those accumulation cycles. The ice keeps getting heavier, bigger and bigger, and that fall at such a rapid rate, it doesn't melt on its way down. That's when you get hail. And that's bad news, really bad news. We're talking about springtime type times, new crops. You get a hailstorm on new crops, no crops, okay? It can be pretty bad. Cars suffer. Roofs suffer. I mean, hail is not a very good thing. It's fun to look at the size of those hailstones, but not unless they're hitting your car. I mean, that's not nice then. Okay, and then finally, all the updrafts are exhausted. Everything's coming down. And boy, do you ever get the rain then. Then it sort of rains itself out, and it's all over, and then the sun comes out, and you have a pretty day after that. If I'm not mistaken, shortly, it seemed like the tornadoes lasted all day long back in April of 11, but the next day was just absolutely beautiful weather, okay, except there was just destruction everywhere, so that made it less than beautiful. But after that, all the updrafts are exhausted and rains itself out and moves on. Okay. Now let's talk a little bit about this. The updrafts, the downdrafts, all this stuff going on in the clouds, circulating precipitation, it separates electrical charges. There's a lot of things moving against each other in opposite directions. Things are rubbing against each other. A lot like combing your hair if, well, those of you who have that, okay, when it's pretty clean and a rubber comb. If you have fairly long hair, do that, and then suddenly you'll see your hair start following the comb as you're trying to, okay. And you think, what's going on here? Same thing that happens in your dryer. All that twisting and bouncing and stuff, and then you pull stuff out of the dryer, and clothes are stuck together. Static cleaning. What's causing that? Electrical charge imbalance. Electrons are getting rubbed off of one air mass onto another air mass, off of one piece of clothing onto another piece of clothing, off your hair onto the comb, and then they try to stick together because unlike charges attract each other. Well, when that's happening here, with the updraft, downdraft, circulating precipitation, separating electrical charges, you get one part of a cloud that's very strongly positively charged, another part of a cloud or a different cloud, an adjacent cloud, that's very strongly negatively charged. After a while, if those charges keep building up, you have discharge. The electrons go from the negative to the positive, okay? And what you call that? Lightning. Sometimes that can be clouds up here, earth down here. Cloud to ground lightning. And actually, I've seen a slow motion shot. It was unbelievable. Ground to cloud lightning. The lightning leaving the ground going to the because the cloud was very strong positive charge, so electrons shot up from the Earth to the cloud. Hey, it can kill you either way. It's just the potential difference that gets you. Okay, actually, it's the amount of charge that gets you. Okay, the charges accumulate in different parts of the thunderhead, and what lightning is discharge between the charge centers. You get a strong positive charge center here, a strong negative there. If they get strong enough and they get close enough, it goes from one to the other. Now, the discharge can be cloud to ground, like I said, ground to cloud, or cloud to cloud. Now, one evening, in the Navy, we had the dog watch. That was around supper time. We had usually 4-hour watches. Midnight to 4 in the morning, the mid watch. 4 to 8 in the morning, that was a pad or 2. 8 to 12, 12 to 4, or 16. But then, over supper time, you had 4 to 6 and 6 to 8. You split that watch so each team could eat supper. And I had, I think, the second dog watch, the 6 to 8. I went up on the bridge, and my word, we were presented with a lightning storm I've never seen. It wasn't anything super bad, but just the clouds were all over the sky, and they were just discharging to each other. It was just like a spider web of lightning. For 2 hours, we stood out there and watched this. There were no other ships around. We didn't have anything else to do. It was just amazing. I don't know what caused it. I guess it was lightning, cloud movement or something, but it was just networks of lightning all over the sky. I've never seen anything like that before. Okay, that's what lightning is. Discharge between charge centers. And that was cloud to cloud that day. Now, when lightning happens, you have enormous amounts of energy moving from here to there. And when that happens, you have ionization taking place. It's heat, and it expands the air like crazy around it, and then it collapses once the charge is moved on. Well, that creates a pressure wave sound. That's what thunder is. The expanding pressure wave from the heated air produces the crack of thunder. Okay. Now, I've asked the class when I've taught this before, can you have lightning with no thunder? Say again? It seems like you do, but not. If you have lightning, there's got to be thunder. It could be the lightning so far away you can see it, but the thunder dissipates before you hear it. Okay? Can you have thunder without lightning? No, there either. You'll sometimes hear it, but never see the lightning because it may be on the other side of the cloud or something like that, and the cloud's blocking you from seeing it. But if you have lightning, you have thunder. If you have thunder, you have lightning. Now, the thing is, the light travels very high rate of speed. Sound travels much slower. So it may be the lightning occurred so long ago you weren't even watching, and then you hear the rumble of thunder later and go, well, there's no lightning with that. Yes, there was. You just never saw it. Or vice versa. You'll see lightning and then not hang around long enough to hear. So you'll always have both. Okay? Can't have one without the other. Okay? Now, here is a sort of a pictorial of what we're talking about. If one part of this cloud is positively charged, meaning it's lost electrons, this part of the cloud is negatively charged, it's gained electrons, then there could be cloud-to-cloud lightning here, cloud-to-ground lightning here, or where there's a positive concentration of charge in the cloud here, that draws, because unlike charges attract each other, it draws negatively charges that were neutral in the ground, draws them up to the surface here, and then they can discharge around the cloud. Or two clouds, not just within one cloud, two clouds, positive and negative, there's another cloud to cloud. And wherever that happens, there is that pressure wave that's got to produce sound. Okay? You may not be close enough to hear it, but it's going to produce sound. Always. Okay. So that was the first. And don't discount thunderstorms. They can be violent. You don't want to mess around with lightning. Okay? You really don't want to mess around with lightning. It seems like there would be a good place to put, what's the safe thing to do with lightning? Anyone know? Say again? Yeah. Well, the best thing is to get down in the ditch, okay? Because you don't want to stand out. You don't want to be a lightning rod, okay? That's the last thing you want to do happen. I can remember growing up on a farm in Georgia, and when we had especially bad thunderstorms that came up suddenly, we would sometimes have a cow that was up on top of a hill. Usually the animal sensed it and got it down. But when it came up really suddenly, and that cow would get struck by lightning, we would use a cow. You know. Other times, the cow might be too close to the fence, and the fence carries the lightning, and if it was close, it discharges to the cow. That's back when we had wooden posts. In more recent years, we went to metal posts, and now we never had that happen after we went to metal posts, but now they had a way to ground really easily and didn't have to go through a cow to get there. So that can happen. It's pretty. So don't discount a thunderstorm. If you hear thunder, there's lightning somewhere, get to safety. You know, get inside if you can. You know. Well, how about under that big old oak tree? You know, that would be safe for it. No, that now is your lightning rod, and you're standing next to it. You could be fried at the same time. Okay, tall trees, not a good idea to be anything any around. That's why ditches are better. Get inside is the best. Okay.
So if you're outside and there is no ditch, you should just lay down?
That's not a bad idea to do. Or make your way to somewhere that you can get shelter, but not under a big tree. Okay. All right, then moving to the next ones, and no one needs to tell anyone in Alabama about tornadoes now. We have had our fair share over the last several years. These are the smallest of your weather situations, but they are the most violent. When you're at one, nothing ranks up with a tornado. Hurricanes much bigger and do more damage, but boy, if you're at a tornado, there's nothing more violent than that, weather-wise. It's a rapidly whirling column of air. Diameter can be from 100 meters. That's the basically goal line to the back of the end zone of the next goal line. That's a pretty big thing. To 400 meters, which is closer, that's at least a quarter of a mile, isn't it? 400 meters, I think it's pretty close to a quarter of a mile. Okay? No, it's more than that. No, that's right. About a quarter of a mile. Okay? Wind speeds up to 480 kilometers per hour, and I don't think in kilometers per hour. Let's just round that to 500, and that would be about 270 to 300 miles per hour. My word, that is fast. You don't want to be out of that. Damage produced by high winds, big time, but also the drop in pressure at the center. Have you ever noticed, when you've seen the destruction of a tornado, how shingles are lifted off of houses, roofs are lifted off of houses, or even houses lifted off their foundation and shifted? That's from the low pressure at the center. Okay? A drop in pressure at the center. Actually, when we talked about violent weather at the first of the term, I said you don't want to be anywhere where there's glass. Now, this is thunderstorms, high winds, tornadoes, or anything, because limbs can be thrown through windows. Okay. If there were no limbs, however, we have limbs here. If there were no limbs, very seldom would. You don't want to be in the upper story anyway, and you don't want to be near the glass. But actually, the windows are usually broken out because the pressure inside the building would be at normal atmosphere. The pressure outside in the center of the tornado would suck the windows out. So the glass usually flies out. But winds would fly in with bringing glass in with it. So don't be in rooms with windows. Okay? Flying debris, that's what I was just talking about. Okay? And these are usually associated with intense thunderstorms. So if you have a really intense thunderstorm, there's a good chance you have a tornado. If you have a hurricane, there's a good chance you have tornadoes being spawned from those thunderstorms that are around the hurricane. So you can have all three if you're very unlucky. Now there's a picture of one. I can't remember where this one was. Texas, I think. Near Dallas, maybe? It's not in this book. It's in the previous book. The one that shows in this book is Marquette, Kansas. I think that occurred, if I'm not mistaken, that may have been like just a month or two after the ones that came through here in April of 2011. There were some that went through Kansas, Missouri, short time after they were here, and it was you thought, goodness, it's going to be all over the country like this. They weren't as bad as ours, but if you're in one, it's bad. Okay. Now, what do you see here? What is this? It's called the funnel cloud. What are you actually seeing? What allows you to see that? This is dust, dirt, debris, anything that is picked up and it sits spiraling upward. In those tornadoes of 2011, we went out in our yard and found, seems like we found letters with Tuscaloosa addresses. We found insulation, who knows where that came from. We found, it was just an amazing array of stuff, a lot of which came from a long way away. That's carrying a lot of stuff with it. Flying debris. That's all they say about tornadoes. I can't believe they didn't have this slide. Let me just make sure they don't show it later. No. Okay. On page 586, okay, I think I'll wait on this one, okay? Let's go on and hit hurricanes, and then we'll do a comparison of the two. So we'll do it that way. Hurricanes. These are also depressions, low pressure areas. Tropical depression, that's where it starts. Most of these tropical depressions, tropical meaning near the equator. Most of the ones that we are concerned with start somewhere over the coast of West Africa. Okay? Either right in here or right in here. This is where they happen. Tropical depressions near the equator. Remember that rising hot air, because of direct solar radiation, rising low pressure, and if it's low enough pressure with the Coriolis effect, it starts to spin. So you start with the tropical depression, area of low pressure. The winds are generally moving at 55 kilometers per hour or less. So that would be, for us, about 30, 35 miles per hour. That's enough to cause you some concern, but, you can handle that. Well, that tropical depression, it can evolve into a tropical storm. Here's what's happening. The pressure gets lower, and the winds get higher. Why? Because the change of pressure creates more wind flow. Okay, so these go hand in glove. The Usually what they measure is the pressure at the in the eye. That determines the category. That correlates really well with the wind speed. So you're hearing talk about wind speed. Really what they use to measure is the pressure at the eye. Okay, so more intense low pressure in the center, and the winds are between 56 and 120 kilometers per hour, which would be about up to 70, 72, 75 miles per hour. Tropical storm. Hurricane, very intense low pressure. If you go back and check some of the biggest of the hurricanes that have gone through, the most damaging ones, check and see what their pressures were. They're way, way down there. In fact, Jerry Tracy had talked about this one of the times we went. He asked what caused the storm surge. Now, I had always been under, remember, low pressures flow in counterclockwise direction. So if it's coming in off the Gulf, this side of the storm is where the hurricane's moving this way and the winds are moving this way. So on this side of the storm, on the east side of the storm, you get the greatest winds. And I thought they just blew the water ahead of them, and that's what was a storm surge. And he said, no, that's a little bit of it, but it's not that much. What the storm surge is where this low pressure, just like it picked up shingles, picked up roofs, picked up houses. This is a big enough change in pressure. It lifts the ocean, lifts the water. That's the storm surge. Then the direction comes from the spinning of the plane. That's why you have the storm surge. Is the pressure is so low, it sucks the water up basically into the eye of the storm. Okay, very intense low pressure. The winds in excess of 120 kilometers per hour, which I think is around 70, 75 miles per hour. Fully developed hurricane has a very calm eye surrounded by the most intense rain and thunderstorm. It's unbelievable that you can have that perfectly calm eye. If you were down here, you couldn't even surf. You know, the water is just perfectly calm. Of course, your ears are probably popping because the pressure is so low, but it's perfectly calm. The highest, strongest winds are right around that wall. So you're perfectly calm here, and you can just see the winds, just blowing by, and intensity unbelievable, and you're in perfect calm. It has to be eerie. And I had a good friend when I was in grad school. He was an undergrad, and he was a forestry major. He liked to be outside. He majored in that. But then the more he, I guess, matured, or maybe thinking about marriage and supporting on a forestry salary or something, his dad had been a pilot for Eastern Airlines. Y'all probably don't even remember what Eastern Airlines was. That was one of the big airlines at one time. And he decided he wanted to fly too. So he became a pilot, got his pilot type, was he probably following his dad, so it wasn't a hard thing for him to get. But at that time, they weren't really hiring much in the airlines. So he went to work for NOAA. Y'all all know NOAA, don't you? National Oceanic and Atmospheric Administration, NOAA. And he flew the planes that went into the eye of the storm and had the crews on of the scientists that were taking all the measurements, the pressure measurements, the wind measurements, all those measurements. That was his job, to fly into the eye of the storm. Now, in the eye, it was probably pretty okay. Getting there and getting out were the bad part, because you had to go way high and go across all that disturbance. That was probably pretty shaky. But in the eye was probably almost nice, especially with a big storm. Now, small storms, the eye sort of collapses and you don't have that thing. You still have to fly into those. Later he got a job, I think, with Delta, and I think retired from there. So anyway, that fully developed eye in a very strong storm, and then storms all around it. Just unbelievable intensity. This is a cutaway view of that storm. In the center, that's the eye. You have almost no activity at all. Calm as can be. No rain, no wind. You're just in there. Perfect calm. Your hurricane force wind, they can go, and these are in kilometers again, from about 20 kilometers out to around 50 maybe. That would be 12 miles to 30 miles out. That's a lot of hurricane wind there. This is a sort of a normal storm. Very low pressure here, so it's sucking down wind like crazy here, and then it gets into the turbulence. Then you have gale force winds outside of there, which can still be a lot of damage. Okay, and this whole thing is spinning like crazy. So sucking down air here and then pulling it up here. Warm, moist air here, pulled up here. The rainfall can be intense around that eye. Really, really intense. Okay. Out here with the gale winds, these can be what spawn tornadoes out here as the hurricane is passing. Now I guess is the place to go back and look at the comparison. You've got it in your text. I can't believe they didn't put it on the slides. Let's compare tornadoes with hurricanes. They both have categories assigned. Tornadoes go 0 to 5, so it's 6 divisions. Hurricanes go 1 to 5, so you have 5 divisions there. And they call it EFI or something like that tornado. EFI 0 tornado. Light damage, winds under 120 kilometers per hour, that's 75 miles per hour. You can have damage to chimneys, tree limbs broken, small trees pushed over, signs damaged. Okay? They claim it was an EF0 that went through our farm in Georgia. I wasn't there. I was here in Alabama. Sort of almost a funny story, unless you were there at the time, and it wasn't quite so funny. My younger brother's oldest child, his daughter, had gone off to law school at Vanderbilt. Okay, and she met a guy there who was also in law school, and he was sharp guy and stuff. We're from pretty different socioeconomic strata, you might say. Now, my younger brother had a good job with the local REA, Rural Electric Association, the power company, not like Alabama or Georgia Power Company, but a smaller one. And he was an engineer with them, so he made good money. I mean, nothing to sneeze at. It was okay. But Tom's father was the head of the pediatrics department at the Ohio State University Medical School. Okay? MD, already stratus apart, head of the department even further apart. So here the Brady's came down to the farm in Georgia to meet the Fowlers, and it was it was a normal spring day, I guess, sort of, but it looked like there could be some rough weather coming later in the day. So my younger brother said, let's go out and look at the farm while we can, because it could be storms later. So they went out and were driving around the farm, and they were in the cow pasture, and they had been talking and stuff, and suddenly they looked around, the cows had disappeared. They had been there, and suddenly they weren't. They didn't notice them leaving, but they weren't around. And there was just some little roar out in the background, and they looked across at the dairy across the road, and there went a tornado down the field. They smartly were fairly close to a ditch in the field. Dr. Brady and his elegant wife and were in the ditch in the field, cow pasture. Who knows how many cow pies down there, hiding from a tornado. And they still got married later. You know, they did, and have had 4 kids since. So you know, everything worked out fine. But it was that EF0 tornado cut a path through my mother's front yard. It was at least, I would say, 35 feet at least wide. You know, just every tree in there. It didn't uproot them all or tear them, but it twisted them all. So later they went in and sawed them all down. But there's this path. She had a wooded front yard, but not. It has a path going up the diagonal. Went up, took out a portion of her magnolia tree, and then curved around the house, only removed a few shingles and shifted a post on the front of the house, went around back and completely obliterated my dad's shed, work building, you know, a concrete block building. I mean, lowered it to the ground. And this was behind the thing, and then went on off into the woods. Okay? It curved around her house and stuff, hardly did that. She had been sitting in the den, and she went out to the porch after it had passed, said, "Boy, this storm really blew some leaves in here." She was out there sweeping the leaves, and they said, "Mom, that was a tornado just came through here." It didn't bother the house at all. EF0, but did all that damage. So it says light damage, you know, damage to chimneys and shed, work buildings, trees, limbs broken, twisted apart, and years later they still have trees dying there because it did enough twisting to the cambium and the whatever you call it, and it just doesn't, the trees don't work well anymore and slowly die. That was EF0. 75-mile-an-hour wind. Let's go over to the hurricane. A minimal hurricane is a Category 1, and it also starts at 75 to 95 miles an hour wind. So this is up to 75, tornado EF0. EF1, moderate damage, this is 76 to 112 miles per hour. That's an EF1 tornado. Category 1 hurricane, 75 to 95. So not too far off, okay? Category 2 tornado, 113 to 155 miles an hour. Well, you're now, that's a Category 2, is 96 to 110. So their 110 mile an hour Category 2, where it ends is where the Category 2 tornado begins, 113. Category 3, 111 miles per hour to 130 miles per hour hurricane. EF3 tornado, 156 to 205 miles per hour. Extreme, Category 4 hurricane, and you don't want to be in a Category 4 hurricane. I believe that's what Katrina finally was when it hit New Orleans. I think it had been a Category 5. It dropped to 4, but still 131 to 155 mile an hour wind. EF4 tornado, 206 to 260 miles an hour wind. EF5 tornado, 261 to 318 mile per hour wind. EF5, or the Category 5 hurricane, catastrophic, is just more than 155 miles an hour. That's an EF3 tornado is more than 155 miles per hour, that's a Category 5 catastrophic hurricane. So you're talking about big differences in wind speed. Of course, hurricanes do far more damage because they're so much bigger. But the intensity of a tornado, nothing touches that. Okay. Did we just pass time to call roll?
Yes.
Yeah, sorry about that. Let me get the roll call before we get too much further, otherwise I'll forget to. Luis is still here. Lexi is still here. Zarik didn't make it in today, did he? Brianna didn't make it in today. CJ's still here. Ethan's still here. Got it. Amanda's still here. Jordan's still here. Jonah and Patrick are still here. Maurice is still here. Cameron's still here. Derek didn't make it in today. Tegan's still here. Kinda anyway. Okay. Chris didn't make it in today. Latricia didn't make it in today. I can't say. Okay. Heaven's still here. Ian's still here mostly. Okay. Edward didn't make it in today. Maya's still here. Michael hasn't heard from him lately. Ken's still here. Diamond's still here. Tamaya, recovering from surgery, she's not here. Ruben's still here. And Ryan's still here. Good deal. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 18, that's 3, 6, 9, 12, 15, 18. Got it. Okay. Now, 23.3, weather forecasting. This begins on the second half of page 587, if you're following in the book. I don't know if things are a little bit better now than when this was put together. They probably are, somewhat. But weather forecasting is based on mathematical models of the atmosphere. That's pretty impressive, right? How did they get these mathematical models of the atmosphere? Now, first, think about what the atmosphere is. The atmosphere is everything from the surface of the earth up. We saw cumulus clouds go to 9 miles up, so they're way beyond that. So the atmosphere goes many, many, many miles up, and it covers the entire globe. Many miles up, covering the entire globe. That's a lot of space. Okay? So we've got mathematical models of the atmosphere. Those have to be enormous models. But you got to have input to make the models, right? So what do they have as input? If my understanding's right, they send up weather balloons from certain locations maybe twice a week. And those weather balloons collect data as they go up and send them back by radio signal. So there's part of the input. Twice a week in one location, miles apart from the next one. That's not a lot of data to basically model. Now, they also, a lot of commercial aircraft and other aircraft are up there in the atmosphere, and with GPS and stuff like this, you can know exactly where they are, and they can send back information to NOAA and other places like that with data, but that's still pretty small. Okay? That's what we've got to base the data on, to base the models on. that's not really the optimal way to model something as enormous as our atmosphere. So there's a bit of a problem. But even with the limited input we have, that creates billions of calculations that necessitate the use of supercomputers. Before we had supercomputers, which I can remember that time because I can remember before we had any computers, super or not, they didn't have the capability of doing this. Okay? All they had were back of the envelope calculations and educated guesses. Okay. Now, I get every time I hear it, I want to, I don't ever do it, but I want to sit down and plot what the 7-day outlooks are really like. Okay? Because fairly accurate forecasts, again, now this is sort of an old slide, but they said they're only up to 3 days if possible. Fairly accurate forecast. And I'd like to, if I had time and energy and really cared about it enough, to sit down and map and see how those 7 days progress through 7, 6, 5, 4, up to 3 days, and see what it is in that 3-day window compared to what it was then. I have a feeling that it was way off. It just gives you a warm and fuzzy about, oh, okay, looks like I can plan for next week. You really can't. They're 3 days, up to 3 days, fairly accurate forecast possible. They may hit it sometimes 7 days out, but they're probably just as likely to miss it 7 days out. The major uncertainty here is insufficient technology to connect the small and the large-scale events together. Because you see, let's take an example. One of my favorite things to listen for, they very seldom refer to it, to listen for is what is the jet stream doing? Does anyone know what the jet stream is? It's where the planes fly, the jet planes fly. They get up into that thing, and if they're going with the jet stream, they can't quite turn off their engines, but they can really be moved along. So that jet stream, that's a large-scale event. What's going on with that? Whereas small scale would be little things like a little thunderstorm popping up here or there, or something like that. How in the world can they connect those, especially since they have such limited input? And even that creates billions of calculation. How can they do this? And have you listened to the weather people lately? I hear James Spann saying this a lot, but Jerry may say it too. We just don't turn on TV much anymore, so I don't hear the weather forecast that much anymore. But they'll say, and thus and so model says this, but this model says this and that. Well, what the problem is, they're very limited in what they can model. And one model will say one thing, and another one will say something else. Given basically the same input, they're just using different algorithms to try to connect them. And none of them are any all that good, but they give us a general idea. That day back in April of 2011, we had a trip to the Weather Center, either that summer term or it was the next fall. I don't remember which it was. But the next time we went there, they had a video of that day and all the things that had happened. And Jerry was saying that just the weather people have this little index that they look at. They look at, wind shears and temperatures and this, that, and the other thing at various elevations. And everything is either contributing or taking away points to their scale. It's a pretty complicated sounding thing. And sometimes surface conditions can be perfect for hurricanes, but if the upper part of the atmosphere things are not so perfect, you're not going to have a tornado. Or vice versa, it can be perfect for a tornado up high, but if the ground conditions are different, nothing's going to happen. He said, this day, when they started looking at the numbers, they didn't know what to do. They had never seen a number that high before. They didn't even know what to predict.
You're talking about April 2011?
Huh?
You're talking about 2011?
Yeah, that April 2011. He said, I can't remember the relative scale. I'm thinking he said something, the number was something in the 600s, and usually they start worrying around 300. And they had just never seen this scale that high. Oh, stand back, folks. We don't know what's going to happen. And boy, was it ever. There's the major uncertainty. Ultimately, the oceanic influences need to be better understood. Now, we'll hit this in the next chapter, son. We know less about the ocean than we know about outer space. Okay? Here we live on the planet. We're surrounded by water on the planet. We know less about the ocean than we do about outer space. And so, yeah, we're nowhere close to this. And things that are going on in the ocean are affecting the weather everywhere. And, boy, our data are severely limited, even with the use of supercomputers. Okay? What do the computer scientists say? Garbage in, garbage out. Unfortunately, the limited data we get coming in sometimes can get close to being garbage. So we don't know what we're predicting out. Certainly nothing beyond 3 days. All right. That was sort of a downer note, wasn't it? Okay. The first half of this chapter has been weather. The second half, and it may not be exactly half, is basically what we call climate. Okay? Are they the same thing? Are those synonymous words, weather and climate? What you think? What's your impression? Close to each other? Okay. Yes.
I need to make a phone call.
Okay.
So
Let's have a little break.
Yeah, is this a good time since it's...
Yeah, it's an excellent time for a break. Okay?
Sorry.
No. You can have all your formula and equation sheets.
Oh, that's what I mean, open book or the formula equation.
You can use either make up a new one or use all your old ones. It doesn't matter. Yeah. Okay. All right.
So wait, so they can use all of them?
Yeah.
They don't have to make one sheet with just...
You don't have to, but actually, I would think it would actually be more efficient to make one sheet rather than having to fumble through 6 or 8 or 9
One
or
sheet
however.
won't hold all that information.
Huh?
One sheet will hold it all.
Yeah, well, but it's going to be a one-page test, so yeah. It's just how well, you can do it however you want to, but you can either use those or make up a single page otherwise. It's going to be a pretty easy test, okay? So let's look at climate, okay? Now, y'all had some time to think on difference in climate and weather. Any ideas? Yes. Very good. Weather is what's happening today. It's warm, not too humid, not too windy. That's the weather today. The climate, like you said, over a longer time scale. Okay? What has been going? It's the composite, larger weather patterns occurring over a number of years. Okay? I was hearing a guy talk last Friday. I actually left campus a little early on Friday so I could go to the, I think I told you all about it. Not everybody was here though. It was a student climate strike. Did y'all hear about that? Okay. And a guy was speaking, I think he was from either UAB or one of the other colleges or universities around, and he was saying there's a really good chance we could go into another drought cycle, which is not good. Because remember, not that many years ago, we were going through one that was, remember Lake Purdy got down to like 20%, that's the water supply for Birmingham. It got down to like 20% or maybe less, at least a couple of times in that cycle. That was sort of scary, you know. And we've had decent rainfall the last several years, but climate would be the larger weather patterns, not just a couple of years, but over the longer. The determining factor in climate, no. Climate is the determining factor in the types of plants and animals at a given location. And this is a pretty interesting way to think of it. I was living in Nebraska for about 5 years. And during that time, I remember hearing people say, I've never seen an armadillo in Nebraska until one of those years or one of those summers. Armadillos were always down in Texas, never in Nebraska. And I can remember on the farm in Georgia, never seeing an armadillo the whole time I lived there, but now they have it. In fact, there was a hole in our the pasture in front of our house that I could have felt like I could have broken a leg in, and my brother said, I think an armadillo did that. You know, I thought, I don't want to meet that armadillo, you know, not at night. Anyway, okay. So, types of plants and animals at a given location. Also, when I was growing up in Georgia, the insects around the cattle, we were trying all sorts of ways to keep the flies and the things from, you know, being a problem. And a couple of the solutions, one in particular that my dad tried, that came out with it and were bragging about it. When he did it, he started having cows go blind because the pesticide that when they knock their heads into it, get into their eyes and they went blind. He quit that. Okay. What he found worked best was a thing he draped and they blew under it and it rubbed down their back, and that did fairly well. But the last several years, probably a decade or so, that we had beef cattle, we never had to mess with that anymore because cattle egrets moved into the area. These big old, awkward-looking, they're almost a crane-looking bird, but beautiful in flight. White, and they all flew in just in magnificent patterns and stuff. They'd just be all there around the cows. Cows would stir up bugs and they would eat them. It was a very synergistic situation. Never had seen a cattle egret my whole life. The time I lived on the farm, started going back, and there were cattle egrets all over the place. Okay? So, types of plants and animals at a given location. That depends on the climate. Things are changing somehow. The types of houses built. What's common with every building except one on this campus? Does anyone think of anything that's common to every building on this campus except one? It's cold. Okay. I haven't been in every building, so I don't know if they're all cold, but I'm talking about the way they're built. Second?
On the slab?
Okay, maybe the second. The roof. What about the roof? Look at the buildings around this campus. They're every one flat. Except the Jesselneer building on the other side of Ethel Hall, when they rehabbed it a few years ago, they put a slanted roof on it because it was leaking so badly. Okay? I don't know, I do know why they do flat roofs, but we can do flat roofs down here. Would they do flat roofs in Switzerland? Why not? Say again? All the snow piled up, they would have bowl-shaped roofs in because they would cave them in. We don't have that problem here. So we could build flat roofs. Not a great idea, I don't think, but you can. But even when we have roofs with pitch, they don't have to be all that great. In Switzerland, they better be great, otherwise too much snow will accumulate and they will have big problems. So in the mountains, they have these really steep A-frame, so the snow. So the types of houses built. And you mentioned slabs. They don't build houses with slabs much in the Northeast. They mostly have basements because they have to get down below the frost line. I'm not sure we have a frost line. You can build a slab house, you can build a crawl space house. They would never in a million years build a crawl space house in the north because then every pipe in there would freeze, you know. They build basement, get down below the frost line for the utilities and everything else to come in. Okay? So the types of houses built. And certainly lifestyles. Okay? How many top flight ice hockey teams do they have in Florida? Probably none, okay? There may be a few somewhere there. We do have one place that has good ice hockey in Alabama. I think. They used to anyway. UAH. Because they had so many people coming in there to NASA, you know, in Huntsville, that they had people who knew how to play. Knew how to skate, you know, and they had ice hockey, okay? You just don't have it down here, okay? But in Canada, it's a national sport, okay? So yeah, lifestyles, not just sports, other things too. Now, what does climate influence? It influences the shape of the landscape. The long-term activities that have gone on, long-term, large-scale weather patterns that have occurred, they shape the landscape. I think we mentioned last chapter about the ice ages. That's a climate issue. That was at the time it may be a weather issue, but that was a climate issue. The glaciers during the Ice Age came across Canada, continental glaciers, swept down into the northern part of the U.S. and ground things to a halt. When they stopped and retreated, that probably when they filled up the Great Lakes, maybe Hudson Bay then, I don't know about that, but they dropped off all that great topsoil that our farms in the Midwest are using now. Thank you, Canada. Okay? But that shaped the landscapes. Okay? Of course, minor things do it less. The types of soil. Climate influences that. Here in the Southeast, remember I was a soil scientist, we have mostly ultisols, meaning ultimate weathering. Okay? They're not the worst of the weathered soils, but they're close to it. Okay? Very low mineral content, very low just about everything because they've been weathered so bad. High temperatures, high moistures. Chemical activity is just eating away at our soil like that. Our farming practices haven't helped any, but just the natural environment. Whereas in Nebraska, Iowa, those places, topsoil, they're mollisols. Those soils, our topsoils we measure in centimeters, millimeters. They measure them in feet there because they just go down forever. They can just bulldoze around, they're still in topsoil. Okay? So types of soil. Highly weathered, low weathered. Again, why up north? Cold in the wintertime, chemical activity basically stops. Okay? Down here, it never stops. Okay? It's always being degraded. Agricultural type and productivity, we were just talking about. They can put so much more corn per acre than we can because their soils will support it. Of course, they may not get the rainfall we do, so that may be an issue. Okay? But then something we can do, they can't do. Double crop. My father used to plant wheat, probably sowed it November, December time frame. It would grow a little bit in the winter time, but as soon as it started getting a little bit warmer days there, it would pop up, and soon you harvest that by May, maybe early into June. And then pile that under and plant soybeans and harvest that in the fall. Whereas in the Midwest, They worked like crazy to get one crop in because the ground wouldn't thaw out until April or May. Then they had to get in there, hoping it wasn't too wet, get it tended and stuff, but they had to get the crop out of the field before October because it was going to freeze by then. So they could only get one crop in, we could double crop. Okay? So agricultural type and productivity. Okay? We couldn't match their productivity, but we could harvest 2 crops a year. Sometimes. Now you could wear out the soil like crazy that way, but yeah. Climate influences lots. Okay? Major climate groups. 2 primary factors here. One is the intensity of the incoming solar radiation. What does that depend on?
Rotation.
Where you are on the globe. If you're near the equator, great intensity. If you're near the poles, very low intensity. In between, you're in between. Okay? That's determined by the angle of incidence of that solar radiation. That's what I was talking about before. The band of the tropics, from the Tropic of Cancer to the Tropic of Capricorn, the greatest, no matter what time of year it is, the greatest intensity of solar radiation, because the angle is almost perpendicular to the ground. The least amount of atmosphere the radiation has to pass through to reach the ground. So greatest intensity reaches the ground. Up here in the temperate area, notice the same radiation comes through a whole lot more atmosphere because it's coming through at an angle. So therefore we don't get, and we're further from it. They're right, makes a difference. Okay? Whereas on the poles, my goodness, they just got glancing shots anyway. Part of the year they don't get any. Okay? Other part is glancing. Okay? So yeah, they never really warm up. It's determined by the angle of incidence of that radiation. So there's one factor, the intensity of the incoming solar radiation. And number 2, the number of daylight hours. Okay. Well, that's certainly related to the same thing, because I think I told you all this. One year, when I taught this course, probably a decade or more ago, I had a woman from Kenya, I believe it was, in the class. I believe it was Kenya. And she said one of the things she had most difficulty with when she came to the U.S., it just was a mystery to her why in the summer we had those long days, and in the winter such short days, because in Kenya, right on the equator, every day was 12 hours of daylight, 12 hours of darkness, year round. It never varied. Okay? Temperatures might vary, rainfall might vary, that kind of stuff. The daylight hours didn't vary. Okay? Here where we live, we did it in one of the labs. Something like, I think we got up to 14, did we? Hours of daylight. Pretty close, more than 14, because it was 9-something darkness. In the summer solstice, in the winter solstice, it's reversed. So, number of daylight hours. That's another thing that contributes to the climate. Okay, or the climate groups that you're in. And all that is based on the tilt of the Earth's rotation axis. How much is that tilt? 23.5 degrees, absolutely. So the equatorial regions receive more solar radiation, greater intensity of solar radiation. The intensity changes on a yearly basis. That is one of the weirder bullet points here. I'm not absolutely certain what they're talking about here. Intensity changes on a yearly basis. I don't think they're talking about the equatorial region. I think they're talking about other regions there. The number of daylight hours varies annually. Not in the equatorial regions. These two, I think, belong separate. I think maybe they should be their own bullets. I just haven't figured out how they messed this one up. Because certainly this is true, and it has almost nothing to do with these two, or not what they're suggesting. Still talking about intensity, but They just don't seem to fit that. They're true statements, but not to deal with the equatorial regions. Okay. So, climate depends in many ways on latitude. The latitude lines, remember? The low latitudes, those are what we're talking about here. These are high solar radiation. They're close to the equator. The yearly variation is small. See, that's why the equatorial region, that last slide didn't make sense. The temperatures are uniformly high. Now, they do have some variations. Mostly the variations come with rainfall. When you're talking about with people in the equatorial region, they usually talk about seasons as being monsoonal seasons. Seasons of heavy rainfall, seasons of light to no rainfall. That's usually what they talk about seasons, not warm and cold. You know, they're talking about wet and dry. Okay? So temperatures are uniformly high year-round. The radiation, yearly variation, very small. The middle latitudes, that's where we live. Okay? That's what I call the temperate region, between the tropics and the Arctics. Okay? The middle latitudes. High solar radiation during one part of the year, our summer, we're still experiencing. What just passed last weekend, or recently? What day did we have?
First day of fall.
Yes, first day of fall, which is often called. Oh, this is several chapters back. Review for the final, right? Say again? Yes, the fall or autumnal equinox. That just happened a few days ago. Okay? I think yesterday was the first full day of fall, if I'm not mistaken. Okay? So, the overall temperatures are lower, but with greater variation than the low latitudes. Yeah, there's some days I bet you we're hotter than it is near the equator. Okay? But there's other days we are in, like in the wintertime, incredibly colder than the equatorial area. In fact, if I'm not mistaken, what I've heard about Hawaii, anyone ever hear much about the weather in Hawaii? You would think that far south, they're down in the tropics. Lots of air conditioning. Not absolutely necessary. Of course, the hotels and things like that have them, and resorts have them. But a lot of people don't have it. They have plenty of wind, and they just open the windows and let those breezes go through, because the temperatures seldom get into the higher 80s. They seldom get below the lower 70s, okay? We're quite often much hotter than it is there. Now, there's a couple reasons for that. The ocean is a huge air conditioner, okay? Remember, high specific heat of water, it keeps the temperature very uniform. Very uniform, okay? So, and then lots of wind. They have the trade winds, they call them, that blow through Hawaii. I think they're mostly east to west winds, because they're near the equatorial region. And they, you know, all the big surf they have there, you know, means a lot of wind coming in. So they don't have to have it. So, but our average temperature is lower than them because they're warm all year long. Okay. In the middle latitudes, the overall temperatures are lower, greater variation than the low latitudes, meaning we can be hotter than the low latitudes, but we can be much, much colder. Now, the high latitudes, however, up in the tropics, the polar regions, okay? North and South polar regions. The maximum amount of radiation is during one part of the year, and it's not very much, okay? Sure, they're pointed toward the sun that part of the year, and they have days with absolutely no sunset. But how high does the sun get those days? Maybe not much more than 20 degrees. At the noon, never sets, but it never is very high in the sky. So you don't have huge amounts of radiation. It comes all day long, but it's still not very much. But then the other half of the year, There are times you get absolutely no radiation at all. When the reverse is happening, you're down here and the sun's here, you don't ever see the sun for days on end. Okay? Maximum amount of radiation during one part of the year, whatever part that summer, is their summer, none in the other, their winter. Overall temperatures are the lowest, but also the widest variation. Now you think we have a lot of variation, going from close to 100 in the summer to maybe as low as the teens in the fall. That seems like, in the winter, that seems like a big variation. But there, anywhere close to 100 in the summer, nowhere close. Maybe 70s in the summer. Lows, maybe even minus 70s. I mean, I don't know. It could happen. When they have absolutely no intensity of radiation coming in. Okay? Widest variation. Here are basically how we split those up. The low latitudes are between the Tropic of Capricorn, 23.5 degrees south, to the Tropic of Cancer, 23.5 degrees north. The middle latitudes between those two, Arctic and Antarctic circles, are at 66.5 north and 66.5 south. So we're the biggest area here, perhaps, at least in number of degrees, upper and lower, north and south. But, well, we're just right in the middle of everything. Now this, as I look at this, is quite accurate, because you remember how close Cuba was to the tip of Florida? I think it's, 90 miles or something like that? Cuba is below the Tropic of Capricorn, and Florida is just above it. So that's called subtropical. We are, Cuba would be tropical. So they don't quite have that one right, but they have it pretty close. Okay. And again, this is showing the angle of, well, that was on the previous slide, the angle of incidence, very direct anywhere in here. Oblique here, and really oblique up here. Huge angle of incidence. Okay. This picture showed it better than just about any of the others. How about we call it there? The climate zones will take a bit of time. They're really closely related to what we were just talking about, but it'll take a bit of time to go over that. So let's make climate zones where we pick up next time. That's on about page 589, close to the middle of the right-hand column, the principal climate zones. Okay. I hope I'm trying to time this out so it'll work out for us. Next time, my prediction is we will finish this chapter, okay, and basically get started on the next chapter. I don't want to get too far along, because I'm hoping that either Tuesday or Thursday of next week we will then have an opportunity to go to Channel 13 weather. And right now I would say I'm leaning more toward Thursday than Tuesday, because Tuesday we probably, if we'll finish this chapter on Thursday, day after tomorrow, then we'll be ready for the test on Tuesday. And I just would guess you'd probably like the test closer to when we finish the chapter. And then you will have studied it and you'll be more ready for the field trip. But if he says come Tuesday, we'll come Tuesday. Or if he says come Thursday, we'll come Thursday. Or even Tuesday of the next week is a possibility. And possibly even Thursday of the next week. If we do Thursday of the next week, that's our last day of period. Okay, so we'll either decide whether to have the final on the Tuesday or have final after we get back from the field trip. But I'm going to hope he either sees us Tuesday or Thursday of next week or the latest Tuesday of the following week. last week of class. How does that sound? Okay. All right, so we'll finish this chapter next week. That means have the test Tuesday of the following week, unless we're at the Weather Center that day. And we'll get started on chapter 24, probably Thursday, and then we'll finish it up, or at least make good progress on it, the day we don't go to the Weather Center. And then we'll have its lab probably the last Tuesday, 2 weeks from today, and then have the final exam 2 weeks from Thursday. Okay, sound okay?
So this
We'll see.
Thursday we're finishing this chapter.
I think we'll finish this
Next
chapter.
But no test.
Yeah, no test on Thursday, no lab on Thursday, so we'll probably not go a full 4.5 hours. Sorry about that, folks. Yeah, get over it. Okay. All right. Y'all ready for the test? Anyone need a little break before the test? Need time to get, let me close this out.